Okay, is there anyone who hasn't got the? I think if you get around 50 something, I think it's still okay. 40, 50 is still okay, but if you get below 30, then it means you need to have a lot of reviews, especially some fundamental concept in mathematics and also calculus 1. Okay, okay, so yesterday I think we discussed the sequence, okay, and then when we discuss sequence, we can state the limit. Okay, we can invert the limit. So write the limit as n approaching infinity, so infinite sequence. And then we can state whether our sequence is convergent or converge, diverge. Okay. Like for example, let me add another sequence. For example, we have a sequence of the. Let's say we have -1 with power of n. Okay. So if we have this is, I think you can imagine, like if we start from 1 and then we increase the n, we see that it will have oscillations, right? It will be -1, 1, -1, 1, and you see that it will also diverge, right? Because we have, it's always changing without consistency, right? So we can say that sequence is divergent. Okay. However, if we take let's say the an is -1 over n. So we take the limit, and because we have this theorem that if we take the limit, okay, so if we can take absolute value, okay, and then if we make sure that it's equal 0, then the limit itself of that sequence will also be 0. So we can do for something that has this sign changing value. Okay, so if you have this -1 with power of n or -1 with power of n minus 1, you can check the absolute value first. Okay, you can check the limit of the absolute value, which means we can take the absolute value which means it's going to be 0. So by theorem, by this theorem, so limit absolute value is 0. Okay, and we can graph this. For example, you could imagine that the graph, if we start from 1, then it will be -1, right? So maybe let me make it a bit higher, maybe here. So let's say -1 is here. So this is n, this is an. So 1 is there, and then when we increase to 2, it will be a positive, but half, right? 1 over 2. So maybe around here, that is 2. So maybe this is 1. So this is will half. So with here, so 1, and then we get 3, but then it is a negative. So it should be around here, and you will see that it's getting closer, and then it reached out the consistency of value that is equal to 0. Okay. So by graphing this sequence, we can tell that this is going to be 0. Or we can use the theorem that, for obvious theorem, that it is also equaling to 0. Okay. And then another theorem that I think also important. Okay. Another theorem that also important is this. So we can say that the sequence, we can imagine a sequence is like a function. Okay. So if we take the limit of the sequence, if this exists as L value, and then the function is continuous at L, then the function of the sequence is equal to with the f of L. Okay. So we can also include the functions. So this we can let's say we have the limit. So by this theorem, if we let this pi over n as our sequence, then we can write the function is our sign, and then we can put the sequence inside the function, and then based on what we have in the limit, it will be 0, so we can state the value is 0. And then another thing is we have the sequence R with power of n. R is some value constant. Okay. So if we want to make this convergent, well, let me write here. So what values of R? So the sequence converge. Okay. So we can say that if we take the limit as n approaching infinity for R, and remember when we have the exponent, like maybe in the calculus you learn about the exponent, either you have the e with power of x or just a normal b with power of x. When we increase the variable, we increase to infinity, then the whole value also increase, right? So if, okay, so there will be at least two conditions. So if R is positive, okay, R is positive, so let me write infinity if R is positive, or maybe to be precise, it's greater than 1. Okay. And then it will be 0, okay, if it's in between 0 and 1. Okay, how do we know this? You could imagine taking some number. Okay, you can take some number, maybe b equal to or b equal half, and you can compare. Okay, you can compare, and you will see that the graphs is going to be This is the exponent like this, right? The positive, you get higher and higher. But when you get negative, you get actually getting closer to 0, right? And then we can write this. So if the r is in between -1, 0, then we have the absolute value of r is between 0 and 1. So the limit of this r we can write as limit, or we can just simply say it's equal to 0. Okay, let me just write there. Okay. And therefore, right here, therefore, limit as n approaching infinity of the r power of n is going to be 0. And what will happen if r equal -1? We already explained with the -1 with power of n, which divergent. Because if you take r -1, it will be -1, 1, -1, 1, -1, 1, and it's always oscillated. Okay? So it's diverged. Okay? Now what's important about this? This will related to later we learn on the geometric series, which are the same formulations, okay, but it's with some summations or with addition. But at least from this r with power of n, you can see how it's two statement. Okay, so when you have r equal 1, okay, for sure that it will state as 1 with power of n, right? It's still 1 power 1, 1 power 2, it's still 1, right? Still 1. And then you say we have the between 0 and 1, of course it will be getting closer to 0. And then, of course, if getting larger than 1, it's getting infinity, right? And then when we have this interval, we set the interval, and then if we check this one here, between -1 and 0, here, if we have r less -1, we can have, I think it's going to be diverge as well. Okay. So, as the conclusions, okay, it will be convergent if we take this interval, okay, without the -1, okay, and then the value, if it's equal 1, it will be 1 if r equal 1, okay, and then if in the interval -1 to 1, the value will be 0, as we mentioned, I think, at the previous explanations. And I think it's quite true. Like, I think if you remember in calculus 1, sometimes we have this notion about the e with power of x and then e with power of -x, right? And then, like, you could imagine, like, this is 1 over e, right? Of course, 1 over infinite is 0. Okay? So you could think from this exponent. Okay, this is the same thing. Okay? The r is actually just any constant. Right? So if we take this, take both of this, take the limit, we can say that this will be infinity. This will be, we can take like that, and it will be equal to 0. Okay. This is just for reference. We can think like in calculus 1 also. Okay. Sometimes some different terms makes confusion, but it's actually similar. We now in chapter 11 we have this R because later we are going to see another R, which in the geometric series. But actually you could think like in calculus 1. And then what else? Okay. Okay. Oh, decreasing and increasing sequence. Okay, let's move to here. So let me explain for a while this part. So we can have a sequence that is always increasing, okay, or maybe it's decreasing. And of course, it's increasing if the previous terms is less than the next term. So an is always less than an plus 1, which means that the function or the sequence is going up. And it's called decreasing if the sequence or the an is greater than the next term. So the next term is lower, so it's going down. Okay, I think it's quite clear from this part here. I think you can just, maybe if you want to write, maybe just this right, increase and then decrease. Okay, and then what else? Oh, the monotonic. So we call monotonic if it is increasing or if it is decreasing. You could, perhaps if you want to look at the word mono means one, so you can just choose one, increase or decrease. Okay. So we call it monotonic. And why is important? Because if you see from any graph from the sequence that we have before, the behavior like this, right? Or maybe to some value like this. Okay, and then we know that it's going to reach out something, right? And we know that it's always decreasing here and then it's always increasing here. And later we know that it is going to be close to some value. Right? We take the limits, right? Take limit as n going large, and then we see that it's consistent on some value. Okay? So that is monotonic. And then if we have some value that is, for example, okay, the value is m. Okay? So if the sequence is always less equal m, it means that it is going bounded above. Okay? It means that here, okay, this m is always on the top. So we call it bounded. Okay? We call it bounded above. Or we use the small m here, and then we switch, and it's always going to be less equal an. So it's going to be down here. So we call this bounded below. So we call it bounded sequence. Okay. So what's the conclusions? Okay. for this monotonic and the bounded sequence. So from this picture, okay, if you see, this is explaining the capital M, okay, and the sequence is going to be reaching the L. So we call this monotonic, it's increasing, and then it's bounded. So the theorem, every bounded and monotonic sequence, they are convergent. It will be converged. Okay. So increasing and then bounded above, it will converge, and then decreasing and then bounded below converges. Also converges. Okay. If you are confusing on the words, you can just focus on these two graph here. Okay. So whenever these two happen, it is converged. Okay. It is convergent. So we say that this is monotonic bounded sequence. Okay. Every bounded monotonic sequence is convergent. Okay, perhaps let me give you some practical applications. So if we want to make sure that, so we have a sequence, let's say 3 with power of n divided n factorial. So we want to know that if this is converged, one way is we try n equal 1, n equal 2, n equal 3. We see the pattern, we see if this is going to be increase or decrease, or maybe something happen in between. So let's try that one first. Okay, let's try, for example, n equal 1. So we have a1, it's 3, and then 1 factorial is 1, so it's 3. And then try n equal 2. And then 2 factorial is 2, and then this, let's say it's 4.5, and then n equal 3, we have 27, and 3 factorial is 3 by 2, 6, right? I think we can divide by 3, it's 9/2, the same, right? So it seems that it starts from 3 and then increase to 4.5, and then start to stay at the same value, right? I think we can make it smaller. And let me make it bigger. And then we start n equal 4, just to see what is going on. And then 4 is 3 with power 4 is 81. And then n factorial, 4 factorial 4, 3, 12, 24, right? And then divide by 3. Okay. This is equal to what? 3.3 perhaps? Yeah, maybe 3.3, almost 4. And then n equal 5. we have 2, 4, 3, and then this will be 1, 20. Okay, and I'm lazy to calculate this, so let me just write that. But at least we see 3 increase, but then it seems decrease, right? So sometimes this might happen. So there is something happening between these two numbers here. Okay. Now, to confirm our theorem, we could set the theorem for the monotonic and bounded, and we need to make sure that this sequence can be fit with the theorem. Okay? So we need to set our an and our an plus 1. Is it less or greater? So perhaps it's going to decrease. Okay? Yeah, it's going to decrease here. Right? You can say at the beginning you can imagine maybe decrease, maybe increase, but we see that if you take another terms and maybe increase the n, you will see that it's going to decrease a lot. You are going to see it decrease a lot. So it's going to be decreased, which means that this is going to be greater or equal. Okay. So let's take this ratio, and then we take our an, put inside, okay, and then we did some calculation here. Okay. Now let me make notes here. If you don't remember that n plus 1 factorial is n plus 1 multiplied with n factorial. Okay. Same. So we can cancel this n factorial, and then we can left out the n plus 1, and then we can also cancel the 3 with power of n with this 3 power of n, because this is actually right here 3, right? So we can cancel this, and then we are getting the 3. Okay, so it turns out that we are having n plus 1 over 3 is greater than 1, and then we can solve this, and then we say that n should be greater or equal to, and then I think it's satisfy what we have in the terms here, which means that we are going to make the n equal 2 as our starting observation. Okay? Because before 2, it seems to increase, but from the n equal 2 and then until the n infinity it's decreasing. Okay? So that's how we get to confirm that, okay, at the n equal 2, it starts to, let's say it's same value, and then decreasing. Okay? Before that, it's increasing. So sometimes there are some sequence that maybe it's going up for a while and then going down, or maybe going down for a while and then going up. Okay. There are some sequences that behave like that. And to make sure that we know whether it's increasing or decreasing, we can set up our relations. So if we think that maybe it's decreasing, maybe it's increasing, and sometimes maybe you need to do some trial. Okay. You can maybe your assumptions is decreasing, or maybe assumption or is increasing, you need to check. You need to check, and then maybe try some numbers. Okay, that easy to compute. Okay? But for proving, we need to use the monotonic theorem. Okay? Monotonic theorem, monotonic sequence theorem. Okay, that's how we get. Okay, now next is the series. Okay, any questions, or do you need to write the sequence before? You still need to write this? Okay, basically you need to check either the sequence is increasing or decreasing, and you need to check whether it's going to be bounded to some certain value.
Professor, can you repeat again how to understand the monotonic theory?
Okay. Okay, so the monotonic said that the sequence, if they go like one way, we call it increasing, right? And if it is go down like that, we call decreasing. Okay, and that is monotonic. Okay, it's either increase or decrease. But if we add the value, like if they have a constant value, for example, they are increasing, but they keep getting maybe closer to 1 or maybe closer to some numbers, we say it's bounded. Okay? So within this theorem here, the monotonic sequence, so every bounded monotonic sequence, they must be converged. Okay? So if you are maybe curious about this, you can check, and maybe you can add maybe n equal 20 or 25. You will see that the number is getting lower and lower and lower, and it seems that the number is getting somewhere near, I think near 0, which means that it is going to be bounded. It's going to be bounded, and from here we say that we can say, maybe let me write here. So after this, okay, after this n. So sequence is monotonic when n is that. Because before n equal 2, it's increasing. Okay? And then after n equal 2, it's monotonic decreasing. Okay? Yeah.
Every sequence that is monotonic is also bounded?
Bounded need to be taken into the limit. Bounded need to be taken into limit. So I didn't write here, so maybe I think in before here, here. So all the limit concept from this part, okay. So if you see from this part here, we need to take that to say the bounded one. So need to check. So bounded need to check the limit. And you can argue from the forms, the denominator is going faster than the exponent, right? So we can argue that this is going to be 0. Maybe sequence is monotonic, maybe decreasing, I forgot decreasing, monotonic decreasing. Okay, let me check if I missed something. Okay, I think we complete. Okay, the next thing is the series. Okay, the series is actually similar to sequence, but we add all the order. Okay. So let's go to the series. So remember that we did this, like the man that who cannot reach the wall. So if we add how much he walks, like from 1/2 plus 1/4 plus 1/8 plus plus 1/2 then we can suggest perhaps that this will be somehow equal to 1. Okay, but this is just our assumptions. Okay, so assume. So this kind of infinite sum of the sequence, we call this a series. So a series is we add all the terms. So we call this infinite series. Or series is also okay. It's also describing the infinite. Okay. And we sometimes describe this in terms of the sigma symbols. Okay. Or sigma with the details like that. And for example, if we may be adding like maybe our sequence is just n, which means that if we take the sum for this an, then if we take start from 1, maybe this will be getting nowhere, right? Maybe it's getting higher and higher, it will be diverged, right? So we start considering the Zeno one here, the first one here, that's starting to sum the distance. So let's start to look at this. And perhaps it's going to be bigger, or maybe let me just write directly to 1/2 power of n. So if we add, for example, if we add n, so this is just 1/2, okay? If we add and then compute this 2 here, this is going to be 3/4, right? Let me write different color. 3/4. And then do the same thing with the third one. What will be? It's 3/4 plus 1/8 is 7/8, right? And you will do the same thing. Maybe you have 1/16. You will have 15/16. So the more n you get, it seems that it's going to be reaching out to 1, right? Maybe you will see maybe 99/100 or maybe some other ratio numbers, but it seems that it's getting closer to 1. Okay? So we can sort, 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 sort using the what we call the partial sums. So let me explain about partial sums. So what we did here is we partially add one by one. So this is when n equal 1, we say it is S1 here. And then we say S2, which means that A1 plus A2. And then we see that we have this 3. It means A1 plus A2 plus A3. But let's make that equation first. So S1 is A1, S2 is A1 plus A2, and then S3 is A1 plus A2 plus A3, and so on and so forth. In general, if we add all this S1 plus S2, or if we take n, it means that we are going to plus A1 plus A2 until some n, right? So we are going to have A1 plus A2 plus A3 until n, like that. And perhaps we can take that as a sum from I equal 1 of AI, like that. So, do I have, okay. So these partial sums, this partial sum here, we have another sequence Sn. So we have another sequence Sn. So S1, S2, S3, right? Which may be having limit or maybe not having limit. So we can write the if limit of this Sn exists, then we call it that this is it's called sum of the series. Okay. Now let me conclude this in a more official definitions. Okay. You can also look at here and maybe. So if you have a series, okay, that an is equal to a1 plus a2 plus a3 plus something until an, or maybe perhaps to make it clear, this is n start from equal 1. We need to reach infinity. So it means that we already said that n getting infinity, right? If we add all, how can we add, right? And now a new idea how to compute all of this is by taking the partial sum. So we take a1 plus we take a1 and then we take a1 plus a2, and then we take a1 plus a2 plus a3, and it's becoming s1, s2, s3 under some sn, which actually it is actually the same, right? It's actually the same. But when we did this, and we can make this sum until some from 1 to n, we can stop the n until here, right? We can make sure, okay, n just stop until here. If we take this, we are not sure how long we can add this, right? Okay. So we set up some these partial sums, okay? And then we can take this as our limit, okay? Because this is another sequence, right? It's another sequence, S1, S2, S3, and we can take that as limit. And if this exists, like one value, like maybe S, and it exists as a real number, then we call the series, because the S the partial sums exist, then the sum we call the convergent. Okay, so it's actually interesting. If we are maybe start from here and not going to the partial sum, maybe we are getting confused how we can add all these numbers. Okay. So we can start to write the convergent as a1 plus a2 plus an plus something else equal to s, or we can just write simply the series of the an is equal to s. Okay. Now we need to distinguish between sequence and series. Every time you see this sum like this, it means that it is a series. Okay. Sometimes, because of different property and behavior, sometimes we can have some mix-up between sequence and series. So the number of s, this is called sum of the series. And of course, if the sequence is diverged, then the series also diverges. So if we cannot find this s, and maybe it's going to be diverged anyway, then the series is called divergent. Okay. And I think I will stop up until that part. We are going to see some examples on the series, and then maybe go for some method. Okay. Okay. So that's all for today's class. If you have any question, please let me know. And I think you can scan this QR.